I want to start today with a question that feels uh, incredibly mundane.
You okay?
Something you've probably done, I don't know, 3 times already this morning without even looking.
Right.
When you plug a device into the wall, your laptop, your phone, toaster, what is actually happening in that split second?
It's the ultimate black box experience, isn't it?
Well,
You plug it in, the magic light turns on, and you go about your day.
yeah.
But if you actually stop and think about the physics of it, that journey from the wall socket to a functional circuit is, it's incredibly chaotic. It's almost violent, really.
Violent is a good word for it. You just take it for granted. But there is this massive war for stability going on inside that little plastic brick.
War. Yeah.
And to understand that war, we're going deep into a very specific, very tactile source today. We are looking at a lecture from Dr. Gadre's Electronic Design Workshop.
And we should set the stage here, because this isn't your standard Intro to Circuits 101 where everyone's just sitting quietly in a lecture hall.
Yeah.
This is the 11th class in the series, specifically for 4th semester ECE students. And the context is crucial. It's a workshop.
Right. You can literally hear the background noise in the recording.
Yeah.
The whole vibe is, well, it's stressed.
Definitely stress. You can tell midterms are looming. These students are expected to build things that actually work, not just, solve equations on paper.
They have to solder. They have to debug.
And they're fully expected to fail. That's part of it.
And Dr. Gadre, he seems to be feeling the pressure, too.
Yeah.
He mentions this list of Nifty 50 topics, these 50 crucial nuggets of engineering wisdom he wants to give them.
Which are great practical skills. Things like how to measure current without blowing the fuse.
Oh, yeah.
That is a rite of passage for every young engineer.
But he has this moment, this realization, early in the recording.
Yeah.
They've only covered 3 of them.
3 out of 50.
And the clock is ticking.
So he has to pivot. He realizes he can't just spoon feed them. He explicitly says, I'm giving you the documentation. You need to learn how to learn.
Which, honestly, is probably the most valuable lesson in all of engineering. But the vehicle for that lesson today, and the core of this deep dive, is Unit 3 of their syllabus.
The power supply.
The power supply.
The heartbeat. I mean, if you don't have stable power, you don't have a circuit. You just have a pile of expensive silicon that does nothing.
So that's the mission. We're going to trace that whole journey from the massive electrical grid all the way down to a single electron moving through a circuit board.
From theory to getting your hands dirty.
But before we even get to the grid, the professor takes this little detour into what he calls Unit 2, the toolkit.
Right.
He starts talking about software, specifically KiCad. Now, for someone who hasn't designed a board before, isn't KiCad just sort of Microsoft Paint for engineers? You just draw the lines where the wires go.
See, that assumption is the trap. That is exactly what Dr. Gadre warns them about.
Yeah.
He emphasizes that the software, it's not just drawing. It's a workflow that connects logic to physical reality.
Okay.
You start with the schematic.
Which is the logical map, the idea.
Exactly. In the schematic, a resistor is just a little zigzag line. It has no size, no weight. It's just an ideal concept. But then you have to assign a footprint. And this is where the footprint trap comes in.
He gave a really specific example of this that I thought was brilliant, the transistor comparison.
Yes, the battle between the BC547 and the MJE2955.
Very catchy names.
Oh, typical engineering. So
Yep.
the BC547 is your standard small signal transistor. It's tiny, it's plastic, it has these flexible little legs. You can bend it to fit almost anywhere.
Okay, I can picture that.
The MJE2955, on the other hand, is a power transistor. It's built to handle heat. So it has a big metal backplate, it's bulky, and its legs are thick and rigid.
Right.
Now, here's the problem. In the software, logically, they both just have 3 pins: base, collector, emitter. So if you just click transistor in the library and don't specify the physical footprint,
You might design a board for the tiny plastic one.
and then you try to jam this massive metal brick into holes that are like 2 millimeters apart, it physically won't fit. The software doesn't know you bought the big one unless you tell it.
So the lesson is that the map is not the territory.
Precisely.
Yeah.
You have to design for the component you actually have in your hand.
So once you have that design, he mentions 2 ways to actually make the board.
Right, the pro route, where you send files to a manufacturer and wait a week.
Or the toner transfer method.
A DIY classic. You print the circuit on a laser printer, you iron it onto a copper plate, and then you dissolve the paper. It's messy, it involves acid.
Fun.
But it's fast, and for a student with a midterm in 2 days, speed is everything.
He also threw in a plug for 3D printing, which I found interesting. He wasn't talking about printing the circuit, but the The enclosure.
Right, the case. Because a naked circuit board sitting on a table isn't a product, it's a hazard. So he encourages them to use STL files, that's the format, and just start printing. But he gives a very practical warning.
Which is?
Know what you are printing.
Meaning, don't start a 12-hour print job when the lab closes in 10 minutes.
Exactly. Understand the density, the infill, just like with the circuit, the physical reality of the plastic matters.
Okay, so we have our tools, we have our board design. Now we need to plug it in. We need to face the grid.
The beast, the ubiquitous source.
And Dr. Gadre brings up this whole global mess of voltage standards. In the lecture, which is in India, it's 220 volts at 50 hertz. But here in the U.S., we're on 110 volts at 60 hertz. I always wondered, is one of them just, like, objectively better? Or is it random?
It's less about better and more about peer pressure. He's very pragmatic about this. He asks the class, why do we drive on the left versus the right?
Because the British did it, or?
Usually, yeah. It depends on who your neighbors were when the grid was built. India followed the European standard, so they got 220V. The U.S., he describes as being an island in terms of standards at the time. We stuck with 110V.
So there's no big physics reason why one is better?
Well, you could argue 110V is a little safer if you touch it, but 220V is more efficient for transmission. But really, it's just convention.
He does give a little nod to the famous Tesla versus Edison war.
Right, the AC versus DC fight. Acknowledging that AC won the distribution battle. But then he drops this one fact that I had completely forgotten about, the aircraft exception.
I love this detail. So airplanes don't run on 50 or 60 hertz?
No. If you could plug your hairdryer into an airplane's internal power, it would probably overheat. Airplanes run on 400 hertz.
That is way faster. Why 400?
It all comes down to weight. It's a pure physics trade-off. To transform voltage, you need a magnetic core, usually iron. The lower the frequency, the bigger and heavier that iron core has to be.
And on a plane, weight is fuel.
Weight is money. By jacking the frequency up to 400 hertz, all the transformers and motors can be made tiny and lightweight. It's brilliant, but it's totally incompatible with your house.
He gives the students an assignment I think we should all do. He tells them to tear apart their old phone chargers.
Void that warranty.
Open it up and just look. But for their class project, they aren't building a phone charger. They are building a linear power supply.
Right.
They need to take that 220 VAC from the wall and turn it into a stable 5 volts DC.
Which sounds easy. You just step it down, right? But Dr. Gadre really stresses that you can't just walk into a shop and ask for 5 volts. You need specs.
Specifically voltage and current.
And the current part is where he catches them in another trap. He asks this trick question. Who consumes more current, a 1 mega ohm resistor or a 1 ohm resistor?
My gut reaction, and I think most people's, is mega. Mega means big, so a mega ohm resistor must use big power.
And that is the fatal flaw. Resistance is the opposition to current. A 1 mega ohm resistor is like trying to drink a milkshake through a coffee stirrer. Almost nothing gets through.
Whereas the 1 ohm resistor?
That's a sewer pipe. It's basically a short circuit. It draws a massive amount of current. So the key lesson is the source doesn't push current. The load pulls it.
Okay, so let's design this supply. We need a transformer. And this is where Dr. Gadre tells that story that just perfectly explains the difference between a textbook and the real world.
The J.J. Colony story.
Yeah.
This was fascinating. So to understand the ecosystem of the city, he actually tried to rent a room in a slum area at J.J. Colony. He wanted to see how the infrastructure really worked.
And he noticed the power was a little unreliable.
That's an understatement. The voltage would fluctuate wildly. It wasn't 220V, it would drop down to 150V, maybe even 140V when everyone came home and turned on their lights.
That's a huge drop. That's almost 40%.
It is. And if you designed your power supply, assuming a perfect 220V input, your device would just shut down every single evening.
So how do you engineer for that?
You build in headroom. If you want a stable 5 volts DC out, you don't start with a transformer that just barely gets you there. You use a 9-volt transformer, maybe even 12V. You create a buffer.
Okay, so we've stepped down to 9V AC, but it's still AC. It's wiggling. We need DC.
Enter the bridge rectifier. 4 diodes arranged in a diamond shape.
I've always had trouble visualizing this. What are they actually doing?
Think of them like one-way gates. As the AC wave tries to go backward, the negative cycle, the diodes flip it and route it forward. So instead of a wave going up and down, you get a wave that just goes up and then up again. You get these humps of positive voltage.
And he gets specific about the parts here. The 1N43001 or 1N4007.
The workhorses of the diode world. But again, specs matter. Those are rated for 1 amp. If your circuit pulls 2 amps, those diodes will physically cook, they will smoke.
He also mentions Schottky diodes, the 1N58110. Why use those?
It's all about speed and efficiency. A standard silicon diode takes a little tax to let current pass, about 0.7 volts.
Doesn't sound like much.
It adds up. That 0.7 volts times your current equals heat. Schottky diodes use different physics, so they only drop about 0.2 or 0.3 volts. They run cooler, and they switch much, much faster.
So for a modern phone charger, you need Schottky.
You have to have them. But for our slow 50 hertz project, the standard 1N407 is fine. It's cheap and robust.
Okay, so we have rectified DC, but it's bumpy.
Yeah.
It's just hump, hump. A microcontroller wouldn't like that.
It would probably crash constantly. Electronics hate humps. They want a flat line, so we need to smooth it out. We need a filter.
The capacitor?
Right. The classic analogy is a water tank. When the hump of voltage comes in, it fills the tank. When the voltage drops between humps, the tank keeps the flow steady. It fills in the valleys.
And Dr. Gadre gives a rule of thumb here. For a 5-volt, 1 amp supply, use about 5,000 microfarad.
Which is a pretty big bucket. But here's where the math can get literally deadly.
Oh.
We used a 9-volt transformer, right? So logically, you'd think, okay, I'll buy a capacitor rated for 10 volts. 10 is bigger than 9. I'm safe.
Sounds reasonable to me.
And that is exactly how you pop a capacitor. Because 9 volts AC is the RMS value, the average. The peak voltage of that sine wave is actually higher.
How much higher?
It's the RMS voltage times the square root of 2, which is about 1.414.
So 9 times 1.414. That's almost 12.7 volts.
Exactly. So your 9-volt line is actually hitting nearly 13 volts over and over. If you used a 10V cap, the insulation inside breaks down, the electrolyte boils, and pop.
So what's the advice?
A safety factor of 2. If you expect 12 volts, buy a 25-volt capacitor. It costs pennies more, and it saves your eyesight.
So now we have a semi-smooth DC voltage sitting around 12 volts. But we want exactly 5 volts. And we want it to stay there.
This is the job of the regulator, and he introduces the celebrity of the regulator world, the 7805.
The 3-terminal linear voltage regulator.
It's so brilliant. Pin 1, input, that raw 12V. Pin 2, ground. Pin 3, output. It basically just burns off the extra 7 volts as heat to give you a perfect 5.0 volts.
Wait, it just burns it?
Yep. That's why it's called linear. It acts like a variable resistor that's constantly adjusting, but the cost is heat. If you touch a 7805 that's working hard without a heatsink, you will burn your finger.
He also mentions the 79 series.
The negative cousins. The 78 series is for positive voltage. The 79 series is for negative.
Why would you ever need negative voltage? I thought ground was 0.
Ground is just a reference point. But think about audio. A sound wave goes up, positive pressure, and down negative pressure. To process that without distortion, your amplifier chips often need a dual supply, like plus 12 volts and negative 12 volts.
And you get that from a center tap transformer.
Exactly. It splits the coil in half, you ground the middle, and you get positive from one side and negative from the other. It's clever.
So we've built the supply, it's regulated, it's stable, but how do we know if it's on?
The user interface. You need indicators.
And he suggests 2.
Right. One on the AC side, the dangerous side. He suggests a neon lamp. Neon needs high voltage to light up, so if that neon is on, death is present in these wires.
Very cheerful. And on the DC side.
A simple LED. But you can't just hook an LED to 5 volts. It'll burn out instantly. You need a current limiting resistor.
And he walks through the math for this. It's Ohm's law.
Yep. Resistance equals voltage divided by current. So you take your source voltage, 5V, subtract the voltage the LED uses.
Which is like 1.8 V for a red one.
Right, so that leaves 3.2 volts. Then you divide that by the current you want, say 10 milliamps, which is 0.01 amps.
So 3.2 divided by 0.01 is 320 ohms.
So you grab a 330 ohm resistor, that's a standard value, and you're good to go. It's simple, but if you guess, you either get a dim LED or a dead one.
Now, before we wrap up, he says something interesting about raw power, that sometimes you don't actually need that 7805 regulator.
Yeah, this comes back to what you actually need. He brings up high-power audio amplifiers. If you need 100 watts to drive a huge speaker, trying to regulate that linearly would generate insane amounts of heat.
And the audio circuits can handle it.
They're pretty robust. They can handle a bit of ripple. They don't need the precision of 5,000 volts like a computer chip, so they just run on raw DC, just rectified and smoothed. It's efficient, but it's dirty power.
So let's just recap the journey we just took.
Okay.
We started at the wall. We acknowledged the chaos of the grid, the JJ colony effect. We stepped it down with the transformer, leaving plenty of headroom.
We rectified it into humps with diodes, making sure they could handle the current.
We smoothed it with a capacitor, remembering the square root of 2 rule so it doesn't explode.
And finally, for our delicate logic circuits, we trimmed it to a perfect 5 volts with a 7805 regulator.
And we added a little LED so we know it's working. It's a complete system.
It is. And what I love is that Dr. Gadre ends with a bit of a teaser. He points out that everything we just talked about is linear regulation. It's simple, it's clean, but it's incredibly wasteful.
Heat.
All that heat. He mentions that the modern world runs on efficiency. The next step is switching regulators. That's what's inside your tiny phone charger. It chops the power up thousands of times a second.
It's complex. It's noisy.
But it's incredibly efficient, which is a deep dive for another day.
Absolutely. So the next time you plug in your phone, just take a second to look at that little brick. It's not just a plug. It's a battlefield. It's fighting the grid, managing heat, and doing calculus just to keep your battery safe.
It really is a marvel of engineering we hold in the palm of our hand every day.
Thanks for joining us on this deep dive. Keep questioning what's inside the box.
See you next time.